Hello and welcome back to another A-Level Maths revision video. Now what I can see here then straight away in the bottom left corner is this video is going to cover some last minute revision here for paper 2, right? Now paper 1 was last week, and for many of you it wasn't really the paper that you were hoping for. And I think that's fair enough. It was a pretty challenging paper, especially the numbers and the working involved. It wasn't the nicest, right? But at this point here, there is no point dwelling on paper 1. My advice from here then is to just focus on papers 2 and 3. The only thing that we can really do here then is just smash papers 2 and 3, right? And hopefully this video here will help you do that. So what I also included here in my video covering my thoughts on paper 1 were some predictions for paper 2, which you can see here on the screen, right? I've included it again. And for this video here, it's over 2 hours and I've included pretty much everything on the screen here with the exception of a few different topics. So what did I not cover in this video here? So nothing on series and summation, which is a little bit annoying, but I will cover those in our predicted paper. So nothing on arithmetic series, recurrence relations, or sigma notation. Nothing on vectors, which again is a little bit annoying. But we did cover a vectors question in our predicted paper 1. I'll also include a second vectors question in our predicted paper 2. So go and check out paper 1 for that vectors question, and nothing on these two here. So nothing on points of inflection, or increasing or decreasing functions. And I think that is pretty much everything that we did include here, with the exception of these starred topics here, right? So hopefully, like I said, by the time you get to the end of this video here, you'll feel a little bit more confident then for paper 2, right? So I don't want to yap for ages here. The last thing that I want to mention then is if you're looking for any last minute revision here for A-Level Maths and paper 2, or even paper 3 here, then head over to our website, AJMaths.co.uk. We have additional revision videos, worksheets, mock and predicted papers here for A-Level Maths, right? There's 10 predicted papers up on our website. So go and check those out. Again, AJMaths.co.uk. And I think that's everything. So, as I said, right, I don't want to keep yapping here. So, best of luck with paper 2 next week. And let's just get started then with question 1. Now, to get us started here then, as we can see on the screen, question 1 is a nice, easy question here on the small angle approximation. So, what we're given here is that theta is small and it's measured in radiators. We're going to use the small angle approximations to find an approximate value of this expression here. So 1 minus cos 4 theta over 2 theta sine 3 theta. So straight away then, I can see the two trig functions here that we're dealing with for this question here is sine theta and cos theta. So we obviously need the approximations for those two trig functions. Now, don't forget them. They are also given in your formula book here. So sine theta. So sine theta is approximately then just theta, right? Nice and straightforward. And then for cos theta here, so cos theta here, that is approximately 1 minus then theta squared over 2. Okay? Like so, there's no tan theta for this expression here, so we don't need any approximation for tan theta. So that's absolutely fine. So let me just start then by writing down the original expression here. So 1 minus cos 4 theta. So 1 minus cos 4 theta all over then 2 theta sine 3 theta. Okay. So this here then will be approximately, so we're going to get 1 minus then cos 4 theta. So because the argument here isn't just theta, we do need to adapt that with the given approximation here. Okay. So basically, wherever there's a theta here in the approximation, replace that now with the new argument here of 4 theta, right? So what I get here, and we'll do this inside a bracket so we don't make any silly mistakes then. We get 1 minus here, so that's 4 theta, and that is all squared. It's not just 4 theta squared, it's 4 theta all squared, like so. That's over 2. And this here then, it's all over 2 theta. So it's 2 theta times sine 3 theta. Well, sine theta is approximately theta. So if the argument changes to 3 theta, then sine 3 theta is approximately 3 theta, right? Nice and straightforward. So it's 2 theta times 3 theta. So let's just simplify this here then. For the numerator, that 1 and this minus 1 here, they just cancel. Osh, I've got minus of a minus here, so that becomes positive. So I've got 16 theta squared over 2, so that's 8 theta squared. So we get 8 theta squared there. That is all over 2 theta times 3 theta, so that's 6 theta squared. So 6 theta squared there. We can now cancel down by the theta squareds here, like so. I get 8 over 6, which is just simply then 4 over 3. So this here then, I put an equal, it should be an approximation here, or approximately. Just to be precise, that is approximately 8 theta squared over 6 theta squared, which is approximately then 4 over 3, right? And there we go. So, as you can see here, a question on the small angle approximations. If we're being truthful, right, people, we shouldn't really be struggling with this. It is pretty straightforward. And normally the small angle approximations are one of the first few questions on the paper. So they're easy marks, right? Don't make a silly mistake with this. And there we go. Bosh, that gives us the solution to question 1. Now moving on to the next question here, question 2. Again, we are keeping things pretty simple, right? So question 2 here, as we can see, then we're given A and B here, which are the following. And all we want to do here is just express each of the following in this form here. So kx to the n, where k and n are just simplified constants. And as we can see here then below, we've got part A, part B, and part C. So again, question 2 here should hopefully be pretty straightforward. It's just on algebraic expressions and indices, right? So again, hopefully nothing too challenging here. So let's just start then at the very top here with part A. So for part A then, we've got A to the power of 1 over 2. So A to the 1 over 2, okay? So A here is 1 over 64 x squared. So I just take A there as it's given, and I raise that to the power of 1 over 2, right? So we've got 1 over 64 x squared, and that then is to the power of 1 over 2, like so, okay? And what we can do here then is think of this in 2 separate parts. I've got the 1 over 64, that's the power of 1 over 2. So if you've got 1 over 64, and that's the power of 1 over 2, right? We just take the square root then of both the numerator and the denominator. So the square root of 1 is just 1, and then the square root of 64 here is 8. So what I get here is 1 over 8. So we get 1 over 8 there. And then for the x squared here, so this is the second part now, x squared raised to the power of 1 over 2. Well, just basic index laws here, right? So the powers are just multiplied together. 2 times 1 over 2 is just simply 1. So what I get here then is 1 over 8, x to the 1, which we just simply write as 1 over 8, x there. Okay, so hopefully nothing too challenging there for part A. Now for part B then, let's just continue underneath here. We might need a little bit more room for part B. So we've got this here, so 16 over b cubed. So 16 over b cubed. So b here is 16 over the square root of x. So let's just write this down here as we're told, right? So 16 over b cubed. So I've got 16 all over. So that is 16 over root x. And this here then is cubed. Okay. So again, just treat the numerator and the denominator separately here. So 16 cubed, just roll it into your calculator, even off the top of your head. Amazing. But either way, that is 4,096. So what I've got here is 16 all over 4,096. And then what I've got here for the denominator then of this fraction is I've got x to the power of 1 over 2. So 1 over 2 raised to the power of 3 then, that is x to the 3 over 2. Okay, so I get x to the 3 over 2 there, like so. Okay, so I've got a number here divided by a fraction. Let's just rewrite that then, just so it looks a little bit neater. I've got 16 times them. I've got 16 times here, x to the 3 over 2. So that's the 3 over 2 there. And this is x to the 3 over 2 over 4,096. Okay. So 16 over 4,096, that is 1 over 256. So what I've got here then is, I don't know why my pen is doing this, by the way. It is really annoying. I'm going to go quickly reset my tablet after this question, but ignore this. So it's 1 over 256. So 1 over 256. And then for the power here, well, we can't do anything with that, right? It's just simply x to the 3 over 2 there. So 1 over 256, x to the 3 over 2. Okay. There we go. Let's quickly get rid of that. It's really annoyed me in a quite a pedantic way, but never mind. So that is equal to that. There we go. We're nearly there. So part C then to finish with here is certainly the most challenging part of this question. Again, my pen is really annoying me. Let's just continue. So I've got AB over 2, and that's the power then of minus 4 over 3. So let's just start with my finding AB here, this product of A and B. So for AB then, let's just write this down here. So AB then, that is A here, which is 1 over 64 x squared, times B, which is 16 over the square root of x, or x to the 1 over 2 there. So what I've got here then is x squared over 64. So x squared over 64. And then I times that here by b, which is 16 over x to the 1 over 2, right? So 16 over x to the 1 over 2 there. Like so, okay? Well, 16 over 64, that's 1 over 4, or a quarter. And then x squared over x to the 1 over 2 here, again, just basic index laws, right? We just subtract here from the power. So 2 minus 1 over 2, that's the same as 4 over 2 minus 1 over 2, giving us 3 over 2 there. So what I get here is, so I get x to the 3 over 2 there, and that is over 4, okay? Now what I've got here is AB divided by 2. So this is AB, so if we divide this by 2 then, it's the same as times it by 1 over 2. So what I've then got here is AB over 2, which is just simply x to the 3 over 2 over 8. So x to the 3 over 2 over 8, like so. So to finish with then, we now just raise this here to the power of minus 4 over 3, and we're done. So therefore then, AB over 2, so AB over 2 to the power then of minus 4 over 3, that is, so I've got x to the 3 over 2 then, so x to the 3 over 2 over 8, and this here then is the power of minus 4 over 3, okay? So to begin with here, let's just deal with the negative power. I'm going to flip this here, so I get 8 over x to the 3 over 2, like so. The power now becomes positive, so 4 over 3. At this point here, I kind of feel like I'm dealing with a GCSE maths problem, but never mind. So let's just start with the numerator here. So 8 to the 4 over 3 then, and that's the cube root of 8, which is 2, and then 2 to the 4 is 16. So we get 16 there for the numerator, and then for the denominator here, x to the 3 over 2, we then raise it to this power here. So 3 over 2 times 4 over 3. Well, the 3's just cancel, and I get 4 over 2 there, giving us x squared, right? So I get 16 over x squared, like so. However, just be careful here. Don't give your solution like this. We want it in this form here, so kx to the n. We've already kind of done that implicitly for the past two, right? So that was 1 over 8 x there. That was 1 over 256 x to the 3 over 2. So for this one here then, just to finish with, make sure that you do give it in the correct form, right? So that's 16 x to the minus 2. Like so. So just be very, very careful for that then, for part C, right? And there we go. It took a little bit longer than I kind of anticipated there for question 2 because it is relatively straightforward. And my tablet is really annoying me, so I'm going to go and quickly restart that then before I continue with question 3. But there we go. So that gives us the solution here to question 2. So question 3 then brings us to the incredibly dull fact theorem, right? So what I'm given here is a function f, which is the following, where a is just a constant. So we're then given that x minus 3 is a factor of f of x. So for the first part here, very standard stuff, right? I just want to show that a is equal to minus 9. So for part A then, let's just do that here at the very top. So a is equal to minus 9. How do we show that then? Well, we just simply use this fact here. That x minus 3 is a factor of f of x, because if x minus 3 is a factor of f of x, then what we know here is that f of 3 is equal to 0, okay? So let's just substitute 3 into this function here, replacing x with 3, right? So what do we get then? So f of 3 here, that is equal to, so we get 2 lots of 3 cubed, 2 lots of 3 cubed, minus 5 lots of 3 squared, plus a times 3. I could have just written that as 3a, but never mind. And then 18, okay? And by the factor theorem here, all of this is equal to 0. So let's just simplify here and let's just see what we get. So 3 cubed, that's 27. Times that by 2, I get 54. That's 54. 3 squared is 9. Times that by minus 5, I get minus 45 there. That's just 3a. I've got plus 18 there. And all of this is equal to 0. So what do I get here? 54 minus 45 is 9. Plus 18, I get 27. So 3a plus 27 is equal to 0. Subtract 27 from both sides here. And it's starting to take shape, right? So 3a is equal to minus 27. And therefore a here is equal to -9, as required, right? So as required there. And we give it a smiley face as always. Happy days. Okay, so that's the solution to part A, hopefully nice and straightforward. Now part B here, it just says factorize f of x completely. So there's a few different ways that you can do this. The first way to do this here is what I call the psycho method. It's absolutely disgusting. And that is to use algebraic long division. So you would take this cubic polynomial here, obviously just replace a with -9, right? And divide that by x minus 3. And that would give you the quadratic factor, right, as part of, this cubic polynomial here. That's the first way to do it, but it's the most disgusting way to do it. Like I said, you can do that, and that is absolutely fine. I'm not kind of saying don't do that, but what psycho enjoys algebraic long division? Definitely not me anyway, so I'm not going to do that. The way that I'm going to do it here is just by inspection. Okay, so what is inspection, I hear you ask? Well, let's just consider here then this cubic polynomial. So I've got 2x cubed. So 2x cubed minus 5x squared plus ax, but a is -9, so that's minus 9x. And plus 18. Now that's equal to, so I've got this linear factor here, so that's x minus 3, like so. And then clearly I'm going to get some quadratic factor here, right? Now, when you multiply through here, so I've got x minus 3 times some quadratic factor here. Then clearly what I need is a 2x squared right at the front, because x times something x squared here must be 2x cubed, so that's just clearly 2x squared. For the final term here, so for the plus 18 then, I can easily see that that must be -6, because -3 times by the constant term here must be plus 18. Well, -3 times -6 is plus 18 there. We get a -6 right at the end there, like so. So how do we get the middle term? This is probably the most challenging part here of part B, really. So there's a couple of different ways that you can do it. But what I will consider here is the x squared term. So what I want here is minus 5x squared, right? So we want minus 5x squared. Okay. Now that is equal to, so once you expand out here, how do we get the x squared terms? Well, I do 2x squared times -3, so that's minus 6x squared. It's minus 6x squared there. If I call this here plus ax, it makes our life a little bit easier, because I know then if I do x times ax here, I get plus ax squared, right? So plus ax squared there. And there's no more ways here to obtain an x squared term, right? So I know then that minus 5x squared here is equal to minus 6x squared plus ax squared, okay? Well, if we just simplify here, add 6x squared to both sides, ax squared here is just simply 1x squared, or just x squared, right? And therefore then, if we compare coefficients here, a is equal to 1. Perfect. So I can now replace this here then with just 1x, or just simply x, right? So to factorize f of x completely here, we know then that f of x here is equal to, so it's x minus 3, the linear factor here, x minus 3 times by the quadratic factor here of 2x squared plus ax, plus just 1x, right? Or just plus x there. And then minus 6, but we can now factorize this here, hopefully, because I've got x minus 3, and then because here, this factorizes to give us, we get 2x minus 3, 2x minus 3, and x plus 2. Yeah, perfect. Good stuff. And there we go. So this here then is f of x factorized completely. As I said, if this method here is for whatever reason confusing, or you don't like it, then that's fine. Just do algebraic long division or any other method here that gives you, a factorized form. But I hate algebraic long division, if you couldn't already tell. So that's my excuse for not doing it. But anyway, there we go. So that's part B done. And then finally, to finish with here, we're given this new function, so g of y, which looks a little bit grim. So it's 2 bracket 3 to the 3y minus 5 bracket 3 to the 2y minus 9 3 to the y plus 18. So it just says then, find the values of y that satisfy g of y being equal to 0. Give me your answers to 2 decimal places where appropriate. Now, what I want you to recognize here is this expression, so this highlighted expression here, looks awfully suspicious and similar to this here, right? And there's a reason for that, because we're going to use that now. And, you know, what we've got here in part A and part B to help us answer part C, right? That's the whole point of doing this question here. So, part C then, I don't have a ton of room. I will try my best to fit it on at the bottom, but let's just see. So for part C then, what I've got here is this, which is 2, basically x cubed minus 5, x squared minus 9x plus 18. Like we said, it's basically the exact same here. The only difference now is we have x is equal to 3 to the y, right? So we now have x is equal to 3 to the y. Like so, okay? So for g of y here, I can now replace that then with the factorized form that we just obtained here in part B, right? So you can see then how using the previous part here is going to be helpful to answer part C. So g of y here, is equal to the following. So I've got x minus 3. So that's 3 to the y minus 3, because x is, 3 to the y. We get 3 to the y minus 3. For the second linear factor here, we've got 2x minus 3. So that's 2 lots then of 3 to the y minus 3. That's 2 lots then of 3 to the y minus 3. And then for the final linear factor here, we've got x plus 2. So that is 3 to the y plus 2. Like so. Perfect. Okay. And then from here, this is equal to 0. Okay, we want to solve this. Well, we've got it in this factorized form here, so we can just solve this, right, for each linear individual factor. So for the first one here, what I've got then is 3 to the y minus 3 is equal to 0. Well, clearly then, 3 to the y is equal to 3. So 3 to the y is equal to 3. So for this to be equal to 3 then, y here must just be 1, right? So therefore, y is equal to 1. Perfect. Okay. So that's the first linear factor dealt with. I'll give that a tick here just so I can see that then. For this one here, I'll just come back to that in a moment. Let's just take a look at 3 to the y plus 2. So for 3 to the y plus 2 here, what that gives me then is, just shade that in, I get 3 to the y is equal to minus 2, right? Now, why is that a problem? Well, clearly here, there are no values of y such that 3 to the y is equal to minus 2. So in other words, we have no solutions here. So no solutions. So that one stinks. Get rid of that. And then finally, we've got this one here. So I definitely don't have a lot of room. Can I fit this on? Yes, if I do it above. Let's just kind of box this off, sorry. So part C, apologies, as you can tell, it doesn't really ever change. My handwriting and my presentation is always awful, but never mind. So for part C then, I'm going to continue at the top here because we've got this solution here, or this linear factor here, that's equal to 0. So I've got 2 bracket 3 to the y minus 3 is equal to 0. So let's just add 3 to both sides here. We get 2 bracket 3 to the y is equal to 3. Just like that. Let's just now divide both sides by 2, right? That gives us 3 to the y. So 3 to the y is equal to 3 over 2. Like so. And we now want to solve for y here, right? Obviously, whatever base you want to take here for your logarithm is absolutely fine, but generally I just prefer to work with the natural logarithm, natty logs. So we take natural logs here with both sides, right? So on the left-hand side here, that would be ln 3 to the y, so I can bring the y down in front here. That gives me y. Ln 3 is equal to ln 3 over 2. So that's y ln 3 is equal to ln 3 over 2, like so. So therefore then, y here is equal to ln 3 over 2 over ln 3. Apologies, by the way, this is really not neat. I hope you can kind of just about follow along. So ln 3 over 2 over ln 3, throw that into your calculator, and we want to give the answers here to 2 decimal places where appropriate. So for this one here then, to 2 decimal places, that is 0.37. So 0.37 there, okay? And there we go. So we get 2 solutions here. We get y equals 1. There we go. And y equals 0.37 to 2 decimal places, right? And there we go. So question 3 did take me a little bit longer than I kind of anticipated there. You know, I'm kind of explaining everything as I go. In an exam, don't explain it as you go, especially not out loud. You'll get thrown out for cheating. But there we go, right? So that gives us the solution here to question 3. Now for question 4 here, this question is really fun because what I've got here is a river that is being studied. Riveting stuff. Do you get it? Never mind. So at one particular place, the river is 50 meters wide. The depth, y meters, of the river is measured at a point x meters from one side of the river. So I've got figure 1 here that shows a plot of the cross section of the river and the coordinate values x, y. So for the first part of this question here then, part A, let's just do this at the very top then. What we simply want to do here is just use the trapezium rule with all of the y values given in figure 1 to estimate the cross-sectional area of the river. Right, so this question here on the surface is pretty straightforward, right? It's just simply an application of the trapezium rule. What might potentially cause problems here is it looks a little bit different. So normally for a trapezium rule question, you're given a table of values. In this question here, you are basically given the table of values, but it looks a little bit different, right? Because what you're given here is the respective points. I've got 0, 0, 3, 1.52, 6, 2.74, blah, 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 so on and so on. Now, if you really want to, you can draw the table of values for x and y, but in my opinion here, it is somewhat unnecessary. I don't think it's really needed. We can just continue from the diagram, right, and the given coordinate values of x and y. So for the trapezium rule here, we need h first to begin with. So h then is the gap here in the x coordinates or the x values. So referring to figure 1 here, I can see then that we go from 0 to 3, 3 to 6, 6 to 9, so on and so on. So h here is 3. So I'll start then by denoting h. So h is equal to 3. So for the area then, A, so A here will be approximately, so the formula is given in your formula book here. I'm just going to do it off the top of my head anyway, but you know, if you do struggle to remember it, just go to your formula book, right? So it's h over 2. So h here is 3, so I get 3 over 2 there. So 3 over 2. And I times this here then by, so we do the first y value and the last y value, but the first y value and the last y value here, they're both 0. So 0 plus 0 is just 0. So I don't even need to bother writing those down. That's absolutely fine. And then we do 2 lots of everything else here. So 2 lots of all of the other y values. So that's going to be then 2 lots here of, so it's 1.52 plus 2.74 plus 3.12 plus 3.08, right? So add all of those together, 1.52, 2.74, 3.12, and 3.08. Like so, close that bracket, we'll close the square bracket as well. So at this point here, just grab your calculator, for all of this into your calc, right? And if you do this correctly, then what you should get here is approximately then for the area here is 31.38 there, right? And this is meters, so it's going to be meters squared here for the cross-sectional area. And there we go. So that's the first part of this question complete. As I said, it's just simply an application of the trapezium rule. So hopefully that doesn't cause too many problems. So that's the first part complete. So for part B then, let's just continue underneath here. What we're now told here then is the water in the river is modeled as flowing at a constant speed of 1.5 meters per second across the whole of the cross section. So for part B then, it just says use the model and the answer to part A to estimate the volume of water flowing through this section of the river each minute. Give me your answer in meters cubed to 2 SF. So what do we do here? Well, it's actually quite straightforward, right? I take my answer from part A, so that's 31.38. Now, what I'm told here is the water in the river is modeled as flowing at a constant speed of 1.5 meters per second. Now, just be careful here because what we want here is the volume of water flowing through this section of the river each minute, okay? So that's minutes. This here is given as meters per second. So you do need to be careful for that, right? So I'm going to times this here by 1.5. So I times that by 1.5, but then, because this is for meters per second here, I times that by 60 because we want this for each minute, right? And the 60 seconds in a minute. So I times that by 60, just like that. And at this point here, then just throw this into your calculator, right? So 31.38 times 1.5 times 60, but just be careful because we want to round the answer here to 2 SF as we're told in part B, right? So if you do this correctly, then what we get here is 2,800. And in terms of the units here, this is meters cubed, right? So 2,800 meters cubed. There we go. So that's the solution to part B, nice and easy. And then finally for part C here, it's just 1 mark, so we shouldn't really be expecting too much work here, right? So it just says then, assuming the model, state, giving a reason for your answer, whether your answer for part B is an overestimate or an underestimate of the true volume of water flowing through this section of the river each minute. Now, if you do struggle to kind of see whether it's an overestimate or an underestimate here, just add to the diagram here. So I'll do it in green. So basically, if you kind of join the vertices together here, right? So this vertex and this vertex together here is a little bit tricky to see. So I won't really do it for that one, but as you kind of go further down here to each vertex, it does become a little bit easier to see, especially with this last one here. So I'll join this one up here. So you join these up with a straight line, right? So like that. And as we can see here, we've got all of this area here that we're not actually including, okay, with our trapezium essentially. Same again here, if you kind of join this up, it should be a straight line, but you got what I mean. I've got this little bit of an area here that we're not actually including. I've got this bit here, again, for my trapezium. So you can see I've got my trapezium here, and we've got this little sliver of area here that we're not actually including. So again, you can kind of see here straight away that it's an underestimate. So what we've got here is an underestimate of the true volume. So this is an underestimate. This is an underestimate. This is an underestimate of the true volume And the reason for that then is because the area of the trapezia are smaller than the cross-sectional area, okay? So again, the reason for this here, this is an underestimate of the true volume because here, the area of the trapezia is smaller, or they are smaller than the cross-sectional area. Okay. And there we go. It does just say give a reason. You can probably do it a little bit more succinctly than I have done here. English was never my strong point, but hopefully that does make sense, right? It's just 1 mark, so it shouldn't really be too much work there. And hopefully you can kind of see then from my diagram here, you know, that the actual trapezium here, trapezii, the area of those is smaller, right? So there we go then. I'm kind of just waffling here, but hopefully that does make sense there, okay? So there we go. That gives us the solution here to question 4. Now for question 5 here, as we can see on the screen then, right, we have figure 2. So figure 2 shows a sketch of the curve with this equation here. So we've got y squared is equal to 2x squared plus 15x plus 10y. Spooky stuff. So for part A then, let's just do this right at the top here. So for part A then, what we want to do here is just find dy by dx in terms of x and y. Now hopefully, what you do recognize here more than anything for this question is that we clearly require implicit differentiation, right? So for the terms here in terms of y, did that make sense? I'm not sure. English is hard. But anyway, this term here and this term here, that's where we require implicit differentiation, right? So to differentiate those two terms, you would just differentiate it like normal. So if it was x squared, that would be 2x, right? And if this was 10x, that would just simply be 10. But once you differentiate those two terms, you also need a dy by dx alongside those. So if I just do that here then, the y squared, as we just said, is 2y but you also need a dy by dx alongside it. So we get 2y. So 2y dy by dx, like so. That is equal to then, so the x squared here, the 2x squared here, that just differentiates like normal, so that's just simply 4x there. So that's just 4x. Same for the 15x here, so that's just plus 15. And as we just said then, the 10y here, that becomes 10 dy by dx. So we get plus 10 dy by dx. Perfect. Okay. Now, at this point here, what I'm going to do then is get everything in terms of dy by dx on one side, everything else over on the other side. So I can subtract 10 dy by dx from both sides here. If we do that then, what we get here is 2y dy by dx minus 10 dy by dx is equal to 4x plus 15. So 4x plus 15 there. And at this point here, let's just take the dy by dx out as a factor. So we get dy by dx outside the bracket, like so. Inside the bracket, we get 2y minus 10, right? The 2y minus 10, like so. And that is equal to 4x plus 15. Lovely jubbly. So I want dy by dx on its own here. So just divide both sides by 2y minus 10, right? So therefore then, dy by dx here, that is equal to, so it's 4x plus 15. 4x plus 15 all over 2y minus 10. Perfect. Okay. And there we go then. Hopefully, nice and easy there, just for part A, right? And that gets us the first 4 marks there for question 5. So for the next part of this question here, then part B, a little bit more abstract here, but I don't think it's too bad. So what we're told here then is the curve is not defined for values of x in this interval here, PQ, as shown in figure 2. So as we can see then, between x equals p and x equals q, it's not defined for values of x, right? So for part B then, it just says, using your answer to part A, or otherwise, find the value of p and the value of q. And basically, you can't use your calculator, so just put it to one side here for part B, right? So for part B here then, how do we find the value of p and the value of q? Well, as it said then, we're going to use the answer to part A here. You can do it in other ways, but I think the easiest way to just use the answer to part A, right? It's the whole point of the structuring of this question. So for part A then, we got dy by dx is equal to 4x plus 15 all over 2y minus 10. Why is that relevant then? Well, what I'm going to find here, or what we are going to find here, is the derivative then is undefined at these endpoints here. So x equals p and x equals q. Well, it's undefined then when the denominator here, 2y minus 10, is equal to 0. So as we just said then, 2y minus 10 is equal to 0. Well, if we just solve for y here, nice and straightforward then, add 10 to both sides, divide by 2, and y is equal to 5, right? So what I'm now going to do here is take this value of y and substitute that back into the original equation here. And let's just see what happens. So I've got y squared, so that's 5 squared, which is 25. That was a funky looking 2, but I'll roll with it. So 25 is equal to 2x squared. I can't do anything with that. So 2x squared. My pen is really annoying me. 15x plus 15x. And I've got 10y. So 10 lots of 5 is 50. So plus 50 there. Like so. Now what I've got here is a quadratic equation in terms of x, right? So obviously the hope here is that we can just solve this quadratic equation for x, and hopefully we can just do that by factorizing. Fingers crossed. So let's just subtract 25 from both sides here. So what I get then is 2x squared plus 15x. And then 50 minus 25 is plus 25. And this here is equal to 0. And as we said then, the hope here is that we can just factorize this, right? And the good news here is we can indeed factorize. If you factorize this quadratic equation here, or this quadratic expression here, what we get then is, we get 2x plus 5. That's for the first bracket here. And then for the second bracket here, we get x plus 5 like so. And again, this is equal to 0. And as we can see, then we get two solutions here, right? So what I get then is, so therefore x is equal to minus 5 over 2, minus 5 over 2. And then from this bracket here, as we can see then, x is equal to minus 5. Bosh. So one of these solutions here corresponds to P. One of these solutions corresponds to Q. Well, hopefully then, it's obvious here that x equals P. P then must be minus 5. So therefore, P here is equal to minus 5. And then for Q here, and Q is equal to the remaining solution, right? No prizes for guessing that. So minus 5 over 2. And there we go. Perfect. So hopefully, I mean, part A was pretty standard. That shouldn't really be causing any issues. Part B is a little bit more abstract. Maybe you haven't seen an example such as this before, but now that you've seen an example such as this here, and hopefully it's not too bad, right? So there we go then. That gives us the solution here to question 5. So for question 6, say we're given these two tasty looking equations that we need to solve then for part A and part B. Now, let's just start with part A here. So for part A then, I'll do this underneath the question here rather than in the top right corner. We do need a little bit of room. As we can see then, we're dealing with natty logs here, or logarithms au natural. So what I've got here is ln of 4 minus 2x plus ln of 9 minus 3x is equal to 2 ln of x plus 1. So if we're going to solve this here then, we're just going to use the laws of logarithms, right? Each log here has the same base. These are all base e, right? It's a natural log. So this should be hopefully somewhat straightforward. Let's just see how we get on then. So because on the left-hand side here, we're adding these two natural logarithms together. They have the same base. Then we can just multiply these together, right? To write this as a single logarithm. So what I get here is ln of, so I put this inside square brackets here just so it looks a little bit neater. I've got 4 minus 2x times 9 minus 3x. So 4 minus 2x times then 9 minus 3x here, like so. So all we've done here then on the left-hand side is just use the laws of logarithms here to express this as a single logarithm. And that is equal to then, so what can we do with the right-hand side here? Well, I've got 2 ln of x plus 1. The 2 now can come up as a power. So what I get here then is ln of, again, we'll just put this inside square brackets just so it looks a little bit neater. So it's x plus 1 squared. Like so, okay? So I've got ln on the left-hand side, and that's equal to ln of something on the right-hand side. So at this point here, we can just antilog, right? So if I antilog here, this ln just disappears. Same with this ln here. So what I get then is 4 minus 2x times 9 minus 3x. Just right underneath then. So 4 minus 2x times then 9 minus 3x. And that is equal to x plus 1 squared. Like so. Okay. So just expand these double brackets here and these double brackets here as well. We're not actually expressing it as a product of brackets at this point here. But that's all it simply is, right? So 4 times 9, that is 36. But what I'll do though is I'll actually give it in order. So minus 2x times minus 3x is 6x squared. We get 6x squared there. I've got, so what have I got here? I've got 4 times minus 3x, that's minus 12x. Minus 12x, and then minus 2x times 9, that's minus 18x there. Like so. And as we said then, 4 times 9 is 36. And that is equal to x plus 1 squared. So that's x plus 1 times itself again. So I get x squared. I've got 2x there as well, of course. So plus 2x and plus 1. So I've just expanded that off the top of my head, but that should be pretty trivial. But just to avoid any potential mistakes, right, you're probably better just writing that as double brackets. It doesn't take too much time, right? So at this point here, I've got a quadratic equation. I can't speak. I've got a quadratic equation. There we go. That's a tongue twister in terms of x. So what I want to do here is make the right-hand side 0, right? So I'm going to subtract x squared, 2x, and 1 from both sides here. So if we do that then, what I get here is 5x squared. So I get 5x squared there. I've got minus 12x. Oh, sorry. So I've got minus 12x minus 8x. That's minus 30x. Subtract another 2x there. That's minus 32x. It does help if you actually simplify beforehand. So there we go, minus 32x. And I've got 36 here. So if I subtract 1 from that, 36 minus 1 is 35. So plus 35. And that is equal to 0. Now, the hope here is that we can just factorize this and just solve for x. And again, we can, right? We can just factorize this here. So factorizing this into double brackets here, what we get then is the following. So in the first bracket here, I get 5x minus 7. I get 5x minus 7 there. Don't do it, pen. Will fall out. And then in the second bracket here, I get x minus 5. Okay, like so. And as we can see then, this will give us two solutions here. So my first solution here is x is equal to, so that's going to be 7 over 5. 7 over 5. And then from this bracket here, you just simply get x is equal to 5, right? Now, that would be a problem because x here is between minus 1 and 2. So we can omit that solution there. And in that case, then, the exact solution here is x is equal to 7 over 5. Let's make a note here that x is between minus 1 and 2. Okay, so we can kind of omit that solution there, like so. And there we go then. So that's a solution to part A involving 90 logs. And for part B then, let's just do this underneath here. I'm hoping we'll have enough room, but let's just see. So for part B then, I've got 2 to the x times e to the 3x plus 1 is equal to 10. So 2 to the x times then e to the 3x plus 1 is equal to 10. Right, so to begin with here then, let's just take 90 logs, or the natural logarithm of both sides here. So I'm going to get ln of, so it's 2 to the x times e to the 3x plus 1, like so, is equal to ln 10, okay? So we've got the natural logarithm here of a product. So that's the natural logarithm of a product here. We can just kind of do what we did in reverse here with part A. So we express this as a single logarithm here because we were adding two individual logarithms with the same base here. So in reverse then, what I get here, let's just continue up here then. I get ln 2 to the x. So ln 2 to the x plus then ln e to the 3x plus 1. And that is equal to ln 10. Perfect. Okay. Now at this point here, you're probably showing at the screen then, ln e, and they just cancel. They're the inverse of each other, and I just get left with 3x plus 1, right? I really can't speak anymore. So I've got ln 2 to the x. Nearly there though with the solution. So ln 2 to the x plus then 3x plus 1, like so, is equal to ln 10. Okay. What I can do here again is just use the laws of logarithms, right? And the x can come down in front of the ln 2. So I get x ln 2 plus 3x plus 1 plus 3x plus 1 is equal to ln 10. Now, at this point here, I've got x ln 2 plus 3x plus 1. So we want to solve for x here. So what I'm going to do then is just get everything in terms of x on one side, and then everything else will be over on the other side, right? So I'm going to subtract 1 from both sides here. So I get x ln 2. So x ln 2 plus 3x is equal to, so they want it in this form here, a plus ln b. So I'm going to do that as minus 1 plus ln 10. Okay. As we can see again, I am kind of running out of room. I should continue a little bit further up here. Apologies. It's not the neatest presentation, but hopefully you can just about follow along. So factoring out the x here on the left-hand side then, I get x bracket then. It's going to be 3 plus ln 2, like so, is equal to, so it's minus 1 plus ln 10. And then finally, we just want x on its own right. So let's just divide both sides by 3 plus ln 2. So therefore then, x here is equal to minus 1 plus ln 10 all over 3 plus ln 2. like so, right? As we can see here then, A, B, C, and D, as we've got them here. So A, B, C, and D, they're all integers, as it's specified then for part B, right? And there we go then. So that would be the next 5 marks there in the bag. So hopefully, I'm not saying that's the easiest kind of, equations there involving logs and exponentials. But again, as A-level math students, these are the kind of things that we shouldn't find too bad. The later questions, they're going to be certainly more challenging, but I don't think this one here is too bad, right? But there we go then. So that gives us the solution here to question 6. All right, so question 7 here, as we can see then on the screen, is on circles, right? What we've got here is a circle C1, which has this equation here. So for the first part of this question here, then part A, parts 1 and 2, we'll just answer those as one, single part here. All we want to do then is just find the coordinates of the center of this circle here, C1, and also the exact value of the radius of C1. So let's just start here at the very top then. So part A, part 1, and part 2. So if we want to find the coordinates of the center of this circle here, and also the exact value of the radius of C1, then what I need to do here is take this equation and get it into the form then of, so it'll be x minus a all squared plus then y minus b all squared is equal to r squared, okay? Once we get it into this form here, the center and the radius is trivial, okay? So how do we get it into this form here? Well, we just need a little bit of completing the square, right? So we start with this equation here. So it's up to you. You can either write down the next step, or you can just go straight into completing the square. But basically what you want to do here is group the x terms together. So it's going to be x squared plus ax. Then group the y terms together. So y squared minus 10y. And that's equal to 29. And then complete the square on the x part. Then complete the square on the y part. Simplify. And we should have it then in this form here. So let me just demonstrate what I mean by all of that, if that doesn't sound familiar. But hopefully it does, right? Because we're days away from our next A-level maths exam. So grouping the x terms, say you get x squared plus ax, then complete the square on that. I get x plus 4. That's all squared. I would then get minus 16. Do the same now with the y part here. So that's y squared minus 10y. That's going to give me y minus 5 there in a bracket. We square that, minus 25, and that is equal to 29. So I now want x minus a squared plus y minus b squared on the left-hand side. So minus 16, minus 25, and then, well, add 25 and add 16 to both sides. That's the easy way to do it, right? So 29 plus 25 plus 16, that gives me 70. So what I've got here is x plus 4 all squared, plus then y minus 5 all squared, that is equal to 70. Bosh, we've got it into this form here. So what I can see here then is for the center, so for the center of C1, that would be then, so it's the opposite to whatever you've got here then inside the bracket. So if it's x plus 4, the x coordinate here for the center of C1 is minus 4. So that's for the x coordinate there. And do the same here then with this bracket. So if it's y minus 5 all squared, then the y coordinate here for the center is positive 5. So it's always just the opposite to what you've got inside the bracket. So that is plus 5 there, like so. So that's the center. That is a part 1 complete. And then for the exact value of the radius of C1 here, well, as we can see then, so for the radius here, so radius of C1, well, r squared is 70, so r here is just simply root 70, right? We can't simplify that, so we'll just leave it as this here. Perfect then. So that's the solution to a part 1 and a part 2. So for the final part of this question here then, part B, let's just do this underneath here. So the circle C2 has this equation. So we've got another circle now. And then for part B here, we want to prove that the circle C1 and C2 neither touch nor intersect here. Another 3 marks for this. Now, for part B here, there is a few different ways that you can do this. You can use substitution and methods such as that. I think the much easier way here is to compare the distance between the centers to the sum of the radii, right? So what is the center here then for the circle C2? So C2 center here So the center here then for C2, that is positive 5 because it's x minus 5. That's 5 and then minus 8, right? So that there is the center for the circle C2. So let's just find the distance then between these two centers here. So I'll do that underneath here. So distance. So this is the distance here then between the centers. So distance between centers. I'll write it in full here just so it makes sense what I'm actually doing. So distance between centers. So how do we find this here then? Well, it's just simply the square root here of, so I'm going to do here minus 8 minus then 5 here. So minus 8 minus 5, and we square this here like so. And we add, and we just do the same here then with the x coordinates. So it's going to be 5 minus then minus 4. So obviously just be careful with the signs here, right? So as we just said then, 5 minus minus 4, that's the same as plus 4. So 5 plus 4 there. And again, that is squared. So let's just simplify this here then. What do we get? So minus 8 minus 5, that's minus 13. So we've got the square root here then of, so that's minus 13 squared, so that's 169. So 169 there. And then 5 plus 4 is 9, so that's going to be 9 squared, which is 81. Got 169 plus 81, okay? So you could write that as 170, you could write that as 80, so that would be 250, so that's the square root then of 250, like so. You can simplify that if you want to, but what I will do here is just write down what this would be as a decimal. You'll see why in just a moment. So this here then is 15.81. Okay, just take it like this for now. And what I also want to do here, as we just said then, is compare this to the sum of the radii, right? So the radius here for C1 was root 70, and then the radius here for C2 is root 52. So radius of C2, that is equal then to, as we just said, root 52, okay? So why are we comparing here then the distance between the centers to the sum of the radii? Well, let's just think about this logically here, right? If the distance between the centers is greater than the sum of the radii, what that means here then is the circles are separate, right? And if they're separate, then C2 or C1 and C2 here don't touch nor intersect, right? So let's just add the radii together here. So the sum of radii, sum of radii, what does that give us here then? So that is root 70 plus root 52. So root 70 plus root 52. Again, what I want here is a decimal for this. So just put this into your calculator, right? If you do this correctly, then what we get here is 15.58. Okay, so as you can see, they are pretty close, but the distance between the centers here is greater than the sum of the radii, right? So let me just make a quick note up here. So 15.81 is strictly greater than 15.58. So what that means here then, as we just said before, is the circles are separate. So therefore then, these circles are separate. The circles C1 and C2 are separate. And therefore then, we can say that this implies that C1 and C2 neither touch. So neither touch nor intersect. Okay. Boom. There we go. So as you can see, the method there, if you haven't seen a question like before, might be a little bit unique, but all things considered, it's not too challenging, right? Just considering distances between centers and the sum of the radii. Mathematically, nothing too challenging. As I also said as well, there's a few different ways that you can do that by considering substitution, going on to find the discriminant. All that kind of good stuff is also absolutely fine there. So if you did use a method such as that, and you obtain the same result here, that the circles C1 and C2 are separate, then that's great. Again, any method here that gets you the solution is absolutely fine. Okay, so there we go then. That gives us the solution here to question 7. Now for the next question here then, question 8, right? As we can see on the screen, we have a question on integration by substitution. Everybody loves integration by substitution. So all we're going to do here is just use this substitution to find the exact value of this integral here, given our answer in the form p plus q ln 2, where p and q are integers to be found. 8 marks for question 8 here. So to begin with then, we just start with this substitution here. So u is equal to, so it's 3 plus then the square root of 2x minus 1. So I'm going to write that as a power, or in index form here. So 2x minus 1, it's a power then of 1 over 2. Okay, because at some point here, we need to rewrite the integrand here. Okay, and we can do that by using this substitution here. We also need to replace dx, right? So to replace dx here, we start with u. We're going to differentiate that here then to give us du by dx and just rearrange and get dx here. So du by dx here. So what does this give us? Well, the 3 is just a constant, so that just differentiates to give us 0. Nice and easy. For this part here, we clearly need the chain rule. So the 1 over 2 comes down in front. We times that by the derivative of the inside of the bracket here. So 1 over 2 times by 2 is just 1. They just cancel out, right? So for du by dx then, all we actually get here is 2x minus 1. But don't forget we reduce the power by 1, so minus 1 over 2 there, okay? And we can just write this here as 1 all over the square root then of 2x minus 1. But what I can also do here is rewrite the substitution here. So if I do that over here then, I know that the square root here, I can't speak today, so the square root of 2x minus 1 is equal to u minus 3. So this here is 1 over the square root then of 2x minus 1, which is just simply u minus 3, right? I've got 1 over u minus 3, like so. And what we want here then, as we said earlier, is just dx, right? So let's just rearrange this here then. So to begin with, let's just take the reciprocal of both sides here. So dx over du. So dx over du, take the reciprocal of this here. I just simply get u minus 3. Like so. And then finally here, dx then is just simply u minus 3 times du, right? So u minus 3 times du. Perfect. Okay. And there we go. So that gives us dx here. And I think at this point then, we now have everything we need then to rewrite this integrand here. Actually, in fact, what I also need here is the new limits. Let's not forget those. So new limits, let's calculate those underneath. So for the new limits here then, we use the original or the old limits here. So when x is 1, what do I get for u here? So u is this here, right? So I get the square root of 2 times 1 minus 1. So that's root 1, which is 1. 3 plus 1 gives us 4. So u is 4 when x is 1. And then when x is 13, what do we get here? Why is my pen doing that? I'm going to fall out of it. So let's try again. I really need a new tablet. There we go. So let's see if we can make it all the way without the pen breaking. When x is 13, then I get root 25, which is 5, plus 3, giving us 8. So u is equal to 8. Perfect. So that gives us the new limits here. So I now think that we have everything that we need then to rewrite the integral. So let's just do that at the very top here. So we have the integral here from 4 to 8. From 4 to 8. So I've got 4 here over the, so I've got 4 all over 3 plus the square root then of 2x minus 1. And 3 plus the square root of 2x minus 1, that is just simply u. So I've got 4 over u. We've then got dx here, and dx then is u minus 3 du. We times that then by u minus 3 du. Okay. And at this point here then, as we can see, this looks a lot nicer to work with, right? So let's just simplify the integrand here. So I've got the integral here then. So the integral here, so just times 4 by u minus 3. So I get 4u minus 12. So 4u minus 12 there. That's over u. We're integrating here then from 4 to 8, so the limits don't change, right? From 4 to 8, okay? And we're integrating here then with respect to u. Well, we can just simplify the integrand again here. 4u over u is just 4. So what I've got here is the integral then from 4 to 8 of 4, what's in a bracket as well, so 4 minus 12 over u. Perfect, okay? Like so, integrating here with respect to u. And at this point here then, this is a trivial integral, right? Just go term by term here. The integral of 4 with respect to u then is just simply 4u. So what I get here, we'll put this inside square brackets because we need to account for the limits, right? So I get 4u there. So 4u. I've got minus 12 over u, so that gives me minus 12 ln u. Okay, so minus 12 ln u there. Perfect. Okay. And we're going from 4 to 8 here. So let's just evaluate the limits here then. We start with the upper limit and we subtract the lower limit. So what do I get here? So I'm going to get then, I'm going to get 4 times 8. So 4 times 8 minus 12 ln 8, like so. We then subtract here the lower limit, right? So I get 4 times 4. So 4 lots of 4 there, minus 12 ln 4, like so. Now we want to give the answer in this form here. So p plus q ln 2, where p and q are integers. So let's just simplify here. 4 times 8 is 32, minus 4 times 4, which is 16. So 32 minus 16 gives us 16, right? So I get 16 here. What I've then got here is minus 12 ln 8, minus 12, sorry, so minus 12 ln 8 minus minus 12, so just be careful for that. So minus 12 ln 8 minus minus 12 ln 4. So I'll just kind of do the working over here then. So minus 12 ln 8 plus 12 ln 4, like so. So what I can do here is take the 12 out as a factor to get 12, and I'll write the ln 4 first. So ln 4 minus ln 8, like so. Because I've got a difference of logs here with the same base, we can express this as a single log. So I get 12. Get 12 ln of 4 over 8, which is 1 over 2. So ln 1 over 2. Now 12 ln 1 over 2 is the same then as 12 ln of 2 to the minus 1, like so. And what I can do here then is bring the minus 1 down in front here. So that gives me then minus 12 ln 2. And notice here then, we've got ln 2 exactly as they wanted here, right? So altogether then, I get 16 minus 12 ln 2. And therefore then, p here is 16. So p is 16 and q here is minus 12, right? And there we go. So p is 16 and q is minus 12. Perfect. And there we go. So another integration by substitution question complete. We covered one in, it was our predicted paper, right? Or was it the last minute revision video? I can't remember off the top of my head. I'll leave a link in the description down below anyway. So go and check those out if you want to have a go, a little bit more practice on integration by substitution. We've also got a full revision video on integration by substitution as well. So go and check that out if you are looking for any extra revision on integration by substitution. But there we go then. That gives the solution here to question 8. All right, so question 9 here is one of those absolutely classic differentiation optimization problems, right? As we can see then on the screen here, we've got figure 4. So figure 4 here shows an open top water tank in the shape of a cuboid, and this is made then of sheet metal. Now the base of the tank is a rectangle, x meters by y meters, and the height of the tank is x meters as well. As we can see then in figure 4. What we're also told here as well is the capacity or the volume of the tank here is 100 meters cubed. So for the first part then of this question here, let's just do this right at the top then. It just says show that the area of the sheet metal used to make the tank is given by the following. So, like I said, a classic differentiation optimization problem. Where do we begin here then? Well, there's two things that we're concerned about here. the capacity, or the volume of the tank here, as we're told then, is 100 meters cubed, and also the surface area here for the sheet metal used to make the tank, right? Now, at some point here, I want to connect both of those, so the volume and the surface area. Let's just start then with the volume here. So V for the volume. Well, if we just look at figure 4 here, it's going to be x times by x, that's x squared there. And then we times that by y. So we get x squared y. Now, as we're told then in the question here, the capacity, or the volume of the tank, is 100 meters cubed. So the volume here, x squared y, is equal to 100. Perfect. Now, at this point here, I won't do anything further with that. If you're familiar with these questions here, you can probably spot what's going to happen. As I said, for now, I'm just going to leave it like so. Okay. And now for the surface area here, let's just call that A. So again, just refer to figure 4 here. So for this face here and this face here, that's going to be x times by x, right? So that's x squared. So x squared, and same again here on this side. Now for the base here, that's going to be x times by y. So that's going to be xy. Now, just be careful here. The same doesn't apply to the top, because if you read the question carefully, it's an open top water tank, right? So the top here essentially doesn't exist for this problem. So the base is xy. And then for the front face here, that's going to be y times by x as well. So that's also xy. As you can see, I've not laid it out in the best way, but hopefully it makes sense. So the front here is xy, and the same also applies to the back of the tank as well. So that's also xy there, okay? So for the surface area here, let's just collect everything together, right? So what I've got here is x squared plus x squared, so that's 2x squared there. So I've got 2x squared, xy plus xy plus another xy. We've got 3xy. Perfect, okay? Now, at this point here, how do we connect the volume and the surface area? Well, as we said before then, if you are familiar with these types of questions here, you probably would have spotted them. I can rearrange here for the volume, make him y the subject, and then just substitute that into this equation here for the surface area, right? So y here is equal to 100 over x squared, okay? And as we said then, we can now just substitute this here into this equation for the surface area. So in that case, then A here is equal to, so I've got 2x squared there. Can't do anything further with that. Then we've got 3xy, but y here is 100 over x squared. So we've got 3x and then y here, which is 100 over x squared, like so, okay? So let's just simplify here. The 3x, when we times through here, well, that x just cancels and reduces this power to 1. And then 3 times 100 is 300 over x. So therefore then, A here, so A is equal to, so it's going to be 300 over x plus then 2x squared as required. Perfect. Okay, so as required there. Happy days. And let's just give it a smiley face. Perfect. Okay, so there we go then. That gives us the solution to part A. Now for part B then, we're going to use a little bit of calculus. So for part B, this will probably take up the rest of the screen here. So let's just see how far we can get. Why is my pen doing that? I don't know. Let's just quickly redo that. Try again. So part B. There we go. I'm being pedantic, but never mind. So it just says use calculus to find the value of x for which A is stationary. So as soon as I see this phrase here, then stationary, I'm thinking of the first derivative being equal to 0, right? So what I want to do here is differentiate A with respect to x, right? So what we want here is dA by dx. Okay, so dA by dx here. So what is that? Well, just go term by term here, right? There's 300 over x. You might find that easier to write that as 300x to the minus 1. So that would be minus 300x to the minus 2, or minus 300 over x squared. And then the 2x squared here, that's just simply 4x, right? So what I get here is 4x minus then 300 over x squared there, like so. Okay, so nice and straightforward then. That's dA by dx. Hopefully nobody struggles with that. But now let's just set this equal to 0, right? As we said before, if it says stationary here, so stationary, that tells us here then that dA, so dA by dx here is equal to 0. So we set this equal to 0 here. And if I set this equal to 0 here then, what I'm going to do here is add 300 over x squared to both sides. So what I've got here is 300 over x squared is equal to 4x, like so. So I've just added that to both sides. Times 3 by x squared then. So what I get here is I get 4x cubed is equal to 300. Then just divide both sides by 4. So x cubed here is equal to 300 over 4, which is 150 over 2, which is 75. And then just take the cube root of both sides here, right? Therefore, x here is the cube root then. So the cube root here of 75. Just throw this into your calculator here, and that gives us 4.217. So 4.217 there, okay? So it doesn't ask for an exact form, so I'm just going to leave it as this decimal equivalent here, but, you know, either's fine, right? So there we go then. That is the value of x for which A is stationary. So that's a solution to A and B. As we can see here, we don't have any more room. So what I'm going to quickly do here is just pause the video, clear the screen, and then we can continue with part C and part D, right? So as we just said then, right, we've cleared the screen here and we can continue with part C and part D. The other thing that I've kept from the previous two parts of the question here, so part A and part B here, is the first derivative, so dA by dx, and also the value of x for which A is stationary. So these are both from part B, right? Because we will need those for part C and part D. So let's just continue then with part C right at the very top here. So for part C then it says, prove that this value of x gives a minimum value of A. Now, what I want to do here then is just determine the nature of the stationary point, right? And to determine the nature of a stationary point here, we do need the second derivative. Okay, so this is dA by dx, and I need to differentiate this here again then with respect to x, right? So for the second derivative here, we have the following. Okay, and again, all we do here is we just go term by term. So the 4x here, that just differentiates to give me 4. Nice and easy, right? And then for this term here, the minus 300 over x squared, you might find it easier to write that as minus 300 x to the minus 2. So what that gives me here then is 600. So it's going to be positive, right? Because it's minus 300 times minus 2. So that's plus 600 there. I get plus 600. And what I get here is x to the minus 3, which is just the same then as 600 over x cubed there. Okay, so I get 4 plus 600 over x cubed. Now, what I need to do here is prove that this value of x gives a minimum value of A. So what we're looking at here is whether for this given value of x here, whether the second derivative is positive or negative. Now for this to be a minimum value of A, what I require here is basically for the second derivative to be strictly greater than 0. It needs to be positive, right? So what I've got here is x cubed. Well, x cubed here, so using x cubed is equal to, so x cubed here would be 75, right? If the cube root of 75 is x, then cube both sides and I get 75. So x cubed is 75 here. And in that case, 4 plus 600 over 75, that's clearly greater than 0, right? So using x cubed is equal to 75, as we can see here, the second derivative of A, which is equal to 4 plus 600 over x cubed, is strictly greater than 0. And because it's strictly greater than 0 here, we have a minimum value of A. So therefore, we have a minimum value we have a minimum value of a. Perfect. Okay. If it was the other way then, so it was 4 plus 600 over x cubed, and that was straight less than 0, then we would have found a maximum value of a. But in this case here, given that we're proving it's a minimum value of a, then, as we would expect here, it's strictly greater than 0. Perfect. So that gives us the solution to part C. And then finally, to finish with here, part D. Let's just continue underneath them. It just says here, calculate the minimum area of sheet metal needed to make a tank. So this is a min here. So all I'm going to do here then is just substitute this value of x, for which a is stationary, because we know this gives a minimum value of a. So all I'm going to do here then is substitute this value of x here into the equation for a. And this will just give us then the minimum area of sheet metal needed to make the tank, right? So a min then is equal to, so it's going to be 300 all over 4.217. So 4.217 like so. And then we have 2 lots of 4.217 squared. So 2 lots then of 4.217 squared like so. Just throw all of this here then into your calculator. And if you do this correctly then, what we get here, it doesn't specify degree of accuracy. So let's just round it to something sensible here. We'll round this to 106.7. So 106.7 there. We're working in meters here, so it's going to be meters squared, right? So 106.7 meters squared. Okay, and there we go then. So as you can see, these types of questions here are relatively straightforward, but there is a little bit of work involved here with these types of questions. So just be careful as you work through it. The most important part really of this question here is part A, and then going on from there, part B, and then part C and part D, right? But as I said, I don't think these questions are particularly challenging. As always, if you are struggling with any point or any part of this question here, just drop us a comment below and I will try my best to help. But there we go then. So that's enough of the yapping here. And that gives us the solution to question 9. Now moving on to question 10 here, as we can see then on the screen, right, we have another question on differentiation. But this time here, it is differentiation from first principles. So what we're given here is that theta is measured in radians. We want to prove then from first principles here that the derivative of sine theta is just simply cos theta. We can assume this formula here, blah, blah, blah. And we can also use these limits here, blah, blah, blah. Standard stuff, right? Now, this is a standard result here. Hopefully you have seen a question such as this one before. If not, I am a little bit worried how you've made it this far. But either way, let's just work through this question together and hopefully it shouldn't be too bad, right? So as always then, with any differentiation from first principles question here, we just start then with f of theta, in this case here, because we're working with theta, right, rather than x, not that it really matters. We also want f of theta plus h, okay? So f of theta here, that is the thing that you want to differentiate here. In this case, in the context of this question, it's sine theta. So f of theta is sine theta. And then f of theta plus h here, that's just simply sine of theta plus h. Like so, okay? So for differentiation from first principles here, don't forget that the result is also given in your formula book. So not something that you do need to worry about memorizing, which is always a bonus, right? So for f prime of theta here, we start by taking the limit then. So this here is the limit. So lim as h tends to 0 of them. So what we've got here is f of theta plus h minus f of theta. And this here then is all over h. Okay. So in that case, then what I've got here is the limit as h tends to 0. F of theta plus h then is sine of theta plus h, right? So sine of theta plus h minus then f of theta, which is sine theta. So minus sine theta. And this here then is all over h. Right, so at this point here, we're now going to use this formula for sine of a plus or minus b. Because this is sine of theta plus h, right? Obviously, just use the correct result as it's given in your formula book here. Let's make a quick note then. sine of theta plus h. As it's given in your formula book here, this is sine theta cos h. So sine theta cos h plus then, so plus here, cos theta sine h. Okay, so we're going to use that here, right? So this then is the limit as h tends to 0 of this here. So that is sine theta. So sine theta cos h plus then cos theta sine h. Okay, don't forget as well the minus sine theta here. Very easy to forget that. So minus sine theta, like so. And again, this is all over h. That was a pretty good straight line for freehand. Perfect. So at this point here, we don't need to start working towards something similar to these two expressions here, right? Sine h over h and cos h minus 1 over h, right? Because we're going to use these limits here at some point towards the end, and hopefully we should obtain then that, the derivative of sine theta here with respect to theta is cos theta. So a little bit of algebraic manipulation is required here. What I will do then is group the sine theta cos h and the minus sine theta together. So we've got the limit here as h tends to 0. I've got sine theta cos h plus cos theta sine h. But as we just said then, let's group this with the minus sine theta. So minus sine theta and then cos theta sine h. So plus cos theta sine h. And again, that is all over h. Again, not too bad for freehand there. So from here then, what I can now do is play the sine theta as a factor, right? So we've got the limit here. Again, as h tends to 0. I know you don't have to tell me, it is tedious, but it is a good habit to get into to do it at each and every step here. So what I will do here then is take the sine theta outside, as we just said. I've got sine theta here, like so. Inside here then, what I get is cos h minus 1. Cos h minus 1, like so. What I'll also do here as well at the same time is split these up then into two separate fractions. So this here then is sine theta cos h minus 1, like so, all over h, like that. That's the first part here. And then we can add here cos theta sine h over h, right? So cos theta sine h all over h. Perfect. Okay, just checking up to this point here. But everything looks good. So what I can now do here then is take outside, well, actually, first, let me split this up then using linearity. So what I can do here is write this then as the limit as h tends to 0 of then, so what I've got here is sine theta bracket cos h minus 1, and that is all over h. So what I'm doing here is splitting this up then as two separate limits. So I've got the first limit there, like so. That's for the first fraction. And then what I've got here is the limit, again, as h tends to 0 of this here. So cos theta sine h all over h, like so. Okay, so let's just go back to the very top here then, because we pretty much run out of room at the bottom. So what I can do here is take the sine theta, so the sine theta here, and the cos theta outside the limits, right? Because sine theta and cos theta are just constants, right? So I can write this here then as sine theta. So it's sine theta times the limit then. Why is my pen doing that? Don't start with my pen. I will headbutt you. So let me just quickly redo all of that. So let's try again. So it's sine theta times the limit here as h tends to 0 of cos h minus 1 over h. And you can start to see then, this is looking pretty good. So I get cos h minus 1 over h, perfect. So cos h minus 1 over h, perfect. And then, again, as we just said before, right, take the cos theta outside as well. We get plus cos theta here. So plus cos theta, times the limit then, again as h tends to 0 of, so I'm going to get sine h over h, right? Sine h over h. And again, as you can see here, this is looking pretty good. So we're now going to make use then of these limits here. So now consider limits. So now consider limits here. Well, this limit here, as h tends to 0, is 0. So what I'm going to get here then is sine theta times 0, because the limit, as h tends to 0 here, of cos h minus 1 over h is 0. And then for this limit here, so as h tends to 0, sine h over h tends to 1, right? So what I've got there then is cos theta times 1. Put these in brackets if you want to, you don't have to, but just to kind of make it a little bit easier to see then once we split those up. Well, sine theta times 0 is just 0. So therefore then, as we can see here, f prime of theta is just simply cos theta times 1, which is just cos theta, right? Exactly as we wanted. So we get cos theta there as required. Perfect. Give it a smiley face. Happy days. Perfect. And there we go then. As you can see, these questions here on paper aren't really challenging. They are long. It's something nearly 10 minutes just to answer this 5-mark question here. And there's a few little things that you do need to be careful of here as you work through the question. But these are quite standard results here. It's not popped up for a few years, so I'm kind of hoping it might pop up on this year's paper 2. If it does, you can call me a genius. If it doesn't, then you can call me whatever name that you want to. But hopefully it will pop up on paper 2, right? Well, there we go then. That gives us the solution here to question 10. Now for question 11 here, then we have a question on quadratic modeling, right? So what I've got here is an archer who shoots an arrow. The height h meters of the arrow above the ground is modeled by this formula here. D is the horizontal distance of the arrow from the archer measured in meters. So we're given here that the arrow travels in a vertical plane until it hits the ground. So for the first part then of this question here, so part A, it just says then find the horizontal distance traveled by the arrow as given by this model. So hopefully it's obvious then that the arrow hits the ground here when h is equal to 0. So when h is equal to 0. So just set the quadratic equation here equal to 0. So what we get here then is minus 0.002 d squared plus 0.4d plus 1.8 must be equal to 0, right? Now, there's two ways to go about this here. You can use the quadratic formula, or you can just use a calculator. I'm just going to use my calculator here because why not? Why would I go through the process of doing this by hand using the quadratic formula? You can absolutely just use a calculator here, and that is fine. You won't get penalized for doing so. Otherwise, I wouldn't do it. I'm not stupid, or not that stupid anyway. So using a calculator here. So using a calculator here, what we get then is two solutions here for D. Well, there's a problem with one of those solutions. So using a calculator here, as we can see then D is equal to, so it's minus 4.4, or D is equal to 204. Okay, that's 204 meters there. Now, this solution here is a problem. Why is that a problem? Well, D is the horizontal distance of the arrow from the arch. Well, if that's negative, then that's clearly a problem, right? So, bosh, get rid of that one. We don't want that one. So, D then is equal to 204 meters. So, the horizontal distance traveled by the arrow, as given by the model, is 204 meters. So, the arrow travels 204 meters there. Okay, there we go then. So that gives us the solution there to part A. Now for part B then, let's just do this underneath here. It just says, with reference to the model, interpret the significance of the constant 1.8 in the formula. So it comes back to this formula here, right? H is equal to 1.8 plus 0.4d minus 0.002 d squared for d greater than or equal to 0. Right, so the 1.8 here, that is just simply the initial height of the arrow above the ground, right? So let's just quickly say that here. So that is the initial height of the arrow above ground, or above the ground, I should say. English is hard. Above the ground. There we go. Perfect. So it's just 1 mark. You don't need a novel for it. That will suffice, right? So that gives us the solution to part B. Now for part C then, we want to write this here in this form here where A, B, and C are constants to be found. Now that might look a little bit spooky, but it is just basically completing the square. Well, it is just completing the square here, I should say, from GCSE maths essentially, right? But it's more difficult because d squared here isn't just 1. I've got minus 0.002 d squared. So that is a problem, and we do need to deal with that. So how do I deal with that then? Well, what I can do here is pull out then minus 0.002 as a factor from the d here, this d term, and also the d squared term, okay? So what I get here then is 1.8. So we get 1.8. Then as we just said, we pull out the minus 0.002 as a factor. So minus 0.002 as a factor. So inside the bracket here then, what I get is minus 200d. So minus 200d and then plus d squared, right? And this is perfect because now that the coefficient of d squared here is just 1, we can now go on to complete the square here. So let's just do that underneath then. I get 1.8 minus 0.002, like so. Now, at this point here, as we just said then, we can complete the square, right? So if you find it easier, right, that's d squared minus 200d. It's the same thing, but you might just see it a little bit easier. But either way, what you should get here is d minus 100. So d minus 100. We square this here, and then you square this here and take the negative of that. So minus 100 squared is 10,000, but we want the negative of that. So minus 10,000. Oops, there we go. So minus 10,000. Perfect. So let me just double check that. Yes, that all looks good up to now. So let's just now times through by the minus 0.002 here. So I get 1.8. So 1.8. I then get here minus 0.002 times d minus 100 squared. So minus 0.002. There's too many noughts here and zeros. It confuses my tiny little brain. And then we times this by d minus 100 squared. So d minus 100 squared, like so. And then we do minus 0.002 times minus 10,000. And that gives us plus 20. So plus 20 there, right? So to finish with here then, just simplify, right? So therefore then, what we get here is 20 plus 1.8. I'm losing my voice, by the way, but let's see if we can make it. So 21.8 minus then 0.002 times d minus 100 all squared. Perfect. As we can see then, we've now got it in this form here. A is 21.8, B is 0.002, we've got D, and then we subtract 100 where C is 100, right? And there we go. So let's just quickly finish here by stating A, B, and C. So A, as we just said then, is 21.8. B here is 0.002. So 0.002. And C here is 100. Perfect. And there we go then. So I guess there's the next 3 marks there, giving us a solution to part C. Now for part D then, the final part of this question here, we've got a little bit more waffle to deal with here. So basically the model is adapted for a different archer, and we get this new formula here. So just compare this then to the original formula. So that's the original formula here, or the original model. And this here is the new model, or the new formula, right? And as you can see then, the only thing that is different here is this constant. So it's 2.1 now. It was originally 1.8. So we'll take that into account in just a moment. So it says then, for part D basically, hence or otherwise find for the adapted model, the maximum height of the arrow above the ground and also the horizontal distance from the archer of the arrow when it's at its maximum height. So for that then, we're just going to use our answer from part C, right? This completed square form to answer part D, because we're talking about the maximum height here, right? So what we need to do here is adapt this then, the completed square form, for the new model. Well, as we can see then, all that happens here is the constant goes from 1.8 to 2.1, right? Increases by 0.3. We just do the same here then with the completed square form. So for the new model here, what we have then is h is equal to, so it's going to be 22.1. So 22.1 minus then 0.002 times d minus 100 all squared, right? That is the only thing that changes here. The constant increases by 0.3. So I'm hoping here it might be obvious what the maximum height is. If it isn't, just think about this equation here for the height, right? Because this is a term that's squared, so it doesn't matter what d is, because we square it, it's always positive. So this is minus 0.002 times a positive number. So we're always going to be subtracting something off, right? So it's going to be 22.1 minus something. So, like I said then, hopefully it's kind of clear here that the only way that we get the maximum height here is when this part is 0, because minus 0.002 times 0 is 0. And in that case then, so this is for D part 1 here, the maximum height then, max height here, is just going to be 22.1, right? So 22.1 meters, okay? Because as we said, in every other situation, we're going to subtract something from it other than when this part here is just 0, okay? So when is it 0? Well, that's when D is 100, right? 100 minus 100 is 0. 0 squared is 0. Then you times it by minus 0.002, and that just gives you 0. So horizontal distance then from the archer of the arrow when it's at its maximum height then, that is when D is equal to 100 meters, right? That's when D is equal to 100 meters, okay? And there we go. So that is quadratic modeling. These types of questions here, they do come up pretty regularly across the A-level maths exam series. So just make sure then that you are confident with quadratic modeling as a topic. I don't think for the most part it's too bad. It is a year 1 topic, so it shouldn't be as difficult as something like integration by substitution or some of those trickier integration questions, you know, parametric integration, parametric differentiation, stuff like that. But there we go then. That gives us the solution here to question 11. Now for question 12 here then, this question is a little bit spicy, right? I won't lie. Part A and part B, pretty standard. That shouldn't really be causing any problems. But part C here is really quite challenging. And you'll see what I mean once we get onto that part of the question a little bit later on. So let's just start then with question 12 here. So this question is really, really interesting. What I've got here is a population of fruit flies that is being studied. So riveting stuff, right? The number of fruit flies F in the population T days after the start of the study is given by this equation here, where K is just a constant. And as it says here then, we must use this equation here for part A, part B, and part C. So for part A then, let's just do this at the very top here. It just says then find the number of fruit flies in the population at the start of the study. So at the start of the study here, that tells us then this is when T is equal to 0, right? So when T is equal to 0 here, what do we get then? So for F here, the number of dinky fruit flies, what I get here is 350. So that's 350e to the 0 because T is 0, right? And that is all over then 9 plus e to the 0. So e to the 0 like so. So that's 350 times 1, which is 350. I then get 9 plus 1, which is 10. 350 over 10. I get 35 there. So the number of fruit flies in the population at the start of the study is 35. So there we go then. Nice and straightforward. That gets us the first mark there in the bag. So for part B then, what do we want to do here? So we're given then that there are 200 fruit flies in the population 15 days after the start of the study. We want to just show here then that K is equal to 1 over 15 ln 12. Right, so what I'm going to do here is take the fact that there are 200 fruit flies in the population 15 days after the start of the study. So what I know here is F is 200 and T here is equal to 15. So let's just substitute both of those in and let's just see what happens, right? So I get 200 is equal to, so it's 350 e to the 15k here. Like so. That is all over there 9 plus e to the 15k. Okay, because t here is 15. So kt, but t is 15. Okay, and we get this here. So at this point here then, I want to get rid of this fraction on the right-hand side. So I'm going to times both sides here by the denominator. So 200 times 9 is 1,800. And then 200 times e to the 15k is 200 e to the 15k, right? So 200 e to the 15k there. And that is equal to 350 e to the 15k, okay? So at this point here, let's just subtract 200 e to the 15k from both sides. What I get here then is 150 e to the 15k is equal to 1,800. Perfect. At this point here, I can't see any silly mistakes. Let's just continue. So I'm going to divide both sides by 150 here. So I get e to the 15k. So e to the 15k here is equal to 1,800 divided by 150, which gives me 12. So we get 12 there. And instantly then, this is looking pretty promising here, right? They've got ln 12 and they've got 1 over 15. I've got a 15 here. And I've got a 12 here. So clearly we're not at the, the correct point here. I haven't got this just yet, but it's starting to take shape. Okay. So what I'm going to do here then is take 90 logs of both sides here, right? So that's going to be ln e to the 15k, which is just the same then as 15k. We get 15k there is equal to ln 12. We take logs or 90 logs of both sides, right? And then finally, what I want here is just k. That's what we're looking to solve for, right? So therefore then, k here, I'm losing my voice, is equal to 1 over 15. So 1 over 15 ln, and that should be 12 there, sorry. So ln 12, there we go. So ln 12. I can't write down basic numbers, but there we go. So that gives us the solution to part B. As you can see then, not too bad up to this point, but part C is where things start to go a little bit crazy. So we will need the full screen here for part C. What I will do then is just quickly pause the video, clear the screen. I'm going to grab a drink because, as you can tell, I'm losing my voice here. So let's quickly pause the video here, clear the screen, and then we can continue with part C. So as we can see then, we've now cleared the screen here, and we've got part C to finish with, right? Now, before we continue with part C here, let's just take a deep breath and say a prayer to our Lord and Savior, Euler. Because part C is absolutely disgusting. What we're given here is when t, or little t, is equal to big T here, the number of stinky fruit flies in the population is increasing at a rate of 10 per day. So for part C here, we want to find the possible values of big T, giving our answers to 1 decimal place. 5 marks for this, right? So this will be fun. First thing here is I see this phrase then, it's increasing. So it is increasing at a rate of 10 per day. What that tells us here then is differentiation is going to be required, right? So what we've got here is f. What I want here then is df by dt, the rate of change. So you want df by dt here. So part C will already be challenging. It'll be even more challenging. My pen decides to keep doing that. Let's just continue here. This is for part C, right? So part C then, we want df by dt here. As we can see, we've got a quotient here of functions. So clearly to differentiate this here, we do require the quotient rule. So for that, I need u and v, and also u prime and v prime clearly. So we'll start with u here. So u then is the numerator. So that's 350 e to the kt, 350 e to the kt there. And then for v here, that is 9 plus e to the kt. Okay, so what I've got here is u, the numerator, and v, which is the denominator. What I also need here then is u prime and v prime. So for u prime here, that is going to be 350k e to the kt, right? because the k is just a constant here, as we're told. So get 350 k e to the kt, like so. And then for v prime here, the 9 is just a constant, so that just differentiates to give us 0. And then what I get here is k e to the kt, right? Again, k is just simply a constant. So we get k e to the kt there, like so. Right, so at this point here then, let's just start to find df by dt. So df by dt here. Will I even have enough room here? I'm not sure. We'll find out. So for df by dt here, we're going to do u prime times v minus v prime times u all over v squared, right? I'll just write down here, otherwise I will forget. So u prime v minus then v prime u, and that is all over v squared, okay? So let me just see if I can fit this on here. Hopefully I can. So what do I get here then? So df by dt is equal to the following. So it's u prime times v. So u prime here is this. We times it by v. So I think the neatest way to kind of express this here then is 350 k e to the kt times then v, which is 9 plus e to the kt, right? So 9 plus e to the kt, like so. We then subtract here v prime, which is this here, times u. So that's going to give me then minus 350 e to the kt. So minus 350 e to the kt times then ke to the kt. So ke to the kt. There's too many k's, there's too many e's, there's too many t's. And that is all over v squared. So at this point here, nothing too crazy, right? So it's just 9 plus e to the kt. At this point here, it's just annoying more than anything, right? Too many e's, too many k's, too many t's, okay? It is easy to trip up, so just be careful, right? So let's just simplify here. How can I simplify then? So I've got 350 k e to the kt times 9. So that is going to give me then 3,150 k e to the kt there. So 3,150 k e to the kt there. So all I've done here is this times by 9. I would then do 350 k e to the kt times this here. But what we do here then is we subtract 350 e to the kt times k e to the kt. So this here is a negative of 350 ke to the kt times e to the kt, right? They just cancel. So all I get left with here then for the numerator is 3,150 ke to the kt. That's fine. And that is all over this here. So don't bother expanding this, right? Just leave it as it is here. So 9 plus e to the kt all squared. Okay. Now this here then is df by dt. But what we're told here then is in this part of the question here. So we're told then that df by dt is equal to 10. It's increasing at a rate of 10 per day. So what I'm going to do here then is set this equal to 10. Like so. Okay. Now, I don't like this fraction here. So what I'm going to do then is times both sides by the denominator. So let's just continue over here on the left-hand side because, like I said, we're going to need quite a bit of room here. So I get 3,150 ke to the kt, ke to the kt is equal to 10 lots then of 9 plus e to the kt. That's supposed to be a bracket, all squared. And rather than trying to expand this out here then, and then times it through by 10, let's just divide both sides by 10, right? Makes more sense to do it that way. Get 315. That should be ke to the kt. I'm getting carried away. So let's try again. I was about to do an e, but I need a k in front of it. So 315 ke to the kt is equal to 9 plus e to the kt all squared, like so. Perfect. So let's now expand these double brackets here. If you find it easier to write this as a product of brackets, I would probably recommend doing that in an exam to avoid any silly mistakes here. I'm just going to do this off the top of my head here because I'm a little bit lazy. So don't be lazy like me. Do it properly. So on the left-hand side, that doesn't change. So I get 315 K E to the KT. Perfect. Now on the right-hand side here, then expanding these double brackets, what do we get here? So I'm going to get 9 times 9, so that's 81. Get 81 there. I get 9 times e to the kt, so that's 9 e to the kt, and we do that again as well in the middle. So 9 e to the kt plus another 9 e to the kt. That is 18 e to the kt. So like I said, it is just easier. You just write down the double brackets. So 18 e to the kt there. And then e to the kt times itself again. So e to the kt. That is e to the 2 kt, right? So e to the 2 kt there. Like so. Right, so where do we go from here? Well, this is probably the most challenging part of the question here to kind of recognize what we do next here. But what I want to do then is just form a quadratic equation here. How do I do that? I hear you ask. Well, what I'm going to do here then is subtract 315 k e to the kt from both sides here. So what I get here then is e to the 2 kt. So e to the 2 kt, like so. I've then got, so I've got 18 e to the kt minus 315 k e to the kt. So what I can do there then is essentially pull out the e to the kt as a factor, okay? Now, because I want this to be a quadratic equation here in terms of e to the kt, I'll write the bracket first so it looks more natural. So what I mean by that then is I get 18, so plus then 18 minus here, so we subtracted this from both sides, right? So 18 minus then 315k, like so. And then we get e to the kt, as we just said, right? We pulled that out as a factor. And plus 81. And all of this here is equal to 0. Right, let's just keep going here. So clearly at this point here, I want to solve this quadratic equation. Yeah, it is grim. There's two ways to really go about this here. So the first way is to use the quadratic formula. Now, we kind of have to just use the quadratic formula no matter what here. But the first way is to use the quadratic formula and then just substitute in the value of k that we had here in part B. We showed it anyway, but even if you couldn't show it, you can still just use this here for part C, right? So we're going to use this here. Let's just kind of highlight that. The second way then is to use the quadratic formula again, but rather than substituting in k by hand, we can just use our calculator. And I'm going to use method 2 here because method 1 is painful, I promise you. So let's just use the quadratic formula here. So this is for e to the kt, right? So e to the kt then, that is equal to then, so what do we get here? So I get minus b, so that's going to be 315k minus 18. Just flip the signs here, right? So 315k minus 18 plus or minus then the square root here. So it's the square root here then of, so we do b squared. So that's 18 minus 315k all squared. Like so. And then we do minus 4 AC. So minus then 4 times 1 times 81. Perfect. And then this here is all over 2 lots of A. So that's 2 times 1, giving us 2 there. Yeah, as you can see, it's not looking pretty. So what I said before then is there's 2 ways to do this. You can just substitute k in by hand here and then just go through all of the algebra to get to a solution, or 2 solutions here. That way, though, is painful in my opinion. So what I'm going to do here is use my calculator now. So it's similar to when you do, iteration on your calculator. What I'm going to do here then is just store this value of k here into the memory of my calculator. So answer here is equal to 1 over 15 ln 12. Okay. And then basically, wherever there's a k here, you replace that with answer on your calculator. So it's going to be 315 answer minus 18. So obviously you need to do this twice, right? So the first one here, I would do plus then, square root here of 18 minus 315, answer all squared, minus 4 times 1 times 81. That's all over 2. And then you need to do the same here with the negative. Obviously, I can't really show you how to do this with a calculator on my screen here. I'm not using an emulator, so I can't really display it on the screen here. So I'm just trusting then that you can do this with a calculator, but hopefully you should get the same solutions as me here. So what I get then is 2 solutions here for e to the kt. So what I get here is e to the kt here is equal to, so I get 31.6215. So 31.6215, or e to the kt here is equal to, so for the second solution here, then we get 2.5615. So 2.5615. So I'm just quickly double check here. I have done all of this correctly. So 31.6215, yes, that's looking good. Then e to the kt here is equal to 2.5615. Yes, perfect. I can't spot any silly mistakes at this point here. So let's just continue then. Now we're looking to solve for little t here. So what we're going to do here then is take 90 logs of both sides here, right? So if we do that on the left-hand side here, we get kt. So kt here is equal to ln of this number here, right? So ln of 31.6215 there, like so. Or k is equal to ln of 2.5615, like so. Okay. Oops, that should be kt there. Apologies. Kt. The question is that long. It has burnt my brain. Can't work anymore. So let's just continue from here. So as we said before, we're looking to solve for t here. Now I've got kt here, but we do know the value of k, right? K is 1 over 15 ln 12. So to finish with here, just divide both sides by k. So therefore then t here is equal to, so it's ln of 31.6215 divided by k. So k here is 1 over 15 ln 12. You might prefer to write that as ln 12 over 15. So that then is the same as 15 ln of 31.6215 over ln 12. You're just using a calculator anyway, so it doesn't really matter, but if you're doing it by hand, that would make it look a little bit neater, but who cares, as long as you get the correct solution. So throw this here then into your calculator. And if you do this correctly then, what we get here for the first solution is 20.8. So 20.8 there. That is to 1 decimal place, by the way, as the question tells us here. So just be careful for that. And then for the second one here, t is equal to, so it's ln of 2.5615. I divide that here then by k, which is again 1 over 15 ln 12. Throw this here then into your calculator again. And if you do this correctly, again to 1 decimal place here, what we get is 5.7. So there we go, we've made it. So to finish with here then, the possible values of t. So the possible values of t are, so it's t is equal to 5.7 days and t is equal to 20.8 days there. Okay, don't forget t here is representing days after the start of the study. And there we go. That part of the question has just took me 16 minutes to answer. Now, don't get me wrong, you can do it quicker because you're not explaining kind of like every step as you go. But yeah, that is pretty challenging. So if you kind of got to that part of the question, you thought, I have no clue what to do here, or you got partway through it and thought, what do I do? That is normal. It is a pretty tricky part to the question. And it is a little bit tedious, but there we go. So that gives the solution to part C and the solution to question 12. Now moving on to the next question here, then question 13, right? We have a question on parametric differentiation and also parametric integration, which is split over 2 different parts, right? So part A then is based on parametric differentiation, where part B is based on parametric integration. So let's just start by quickly reading through the question. So what I can see here then is we have figure 3, this beautiful diagram, right? In this question here, you must show all stages of your working, blah, blah, blah. We don't care. So a curve C has the following parametric equations here for t between 0 and pi over 2. So The point P with parameter t is equal to pi over 4 lies on the curve C. The line L is a normal to C at the point P, as we can see here in figure 3. So for the first part then of this question here, so for part A then, it just says, show using calculus that an equation for L is the following here. 5 marks for this, right? So as we've already said here, part A will require parametric differentiation because we clearly require a gradient. But before I do anything to do with parametric differentiation here, let's just find then the coordinates here for the point P, right? So for the point P here, that is when t is equal to pi over 4, okay? So when t is equal to pi over 4, what do we get here then for x and y? So x here, that is going to be sine squared pi over 4. We get sine squared pi over 4. Just roll this into your calculator, we get 1 over 2 there, like so. And then for y here, so y is 2 tan, so 2 tan pi over 4. Well, tan of pi over 4 is 1, 2 times 1 gives us 2. So the point P here, so P has coordinates then of 1 over 2 and 2 there, okay? Perfect. So we can now start with the parametric differentiation here because clearly at some point here, I will need the gradient. So what I want here is dy by dx. Okay, so we want dy by dx here. Why is my pen doing that? Honestly, guys, I need a new pen, possibly even a new tablet at this point here. This one might be broke. But anyway, let's just see if we can make it. Why is my pen red as well? There we go. So, that's really annoying. So, dy by dx then, what is that? So dy by dx here, well, this is parametric differentiation here. So for dy by dx then, what I want here is dy by dt, so dy by dt times then dt by dx, right? As you can see here, the dt's would just cancel and we'd just get dy over dx there, okay? So what I want to find here is dx by dt and also dy by dt. So dx by dt here, what is that? So dx by dt here, clearly we do need to use the chain rule here, so just take your time with this, you don't need to rush it or anything like that. It should hopefully be pretty straightforward. So for dx by dt here, I get 2 in front, so I get 2 sine t and also cos t there as well. So 2 sine t cos t, like so. So that's dx by dt there. And what I also want here is dy by dt. So for dy by dt, I'll do it on the same line here. And dy by dt here, what does that give us? So dy by dt here, differentiating y with respect to t here, I get, so it's going to be a standard result here, so just refer to your formula book, but what I get here is 2 sec squared t. So 2 sec squared t. Perfect. So for dy by dx here, so therefore dy by dx here, that is going to be then dy by dt, which is this here, so 2 sec squared t, times then dt by dx. Now, this is dx by dt, so for dt by dx, right, we just take the reciprocal of this. So we times it by 1 over 2 sine t cos t. So that's just the same then as 2 sec squared t over 2 sine t cos t, like so, okay? So just throw then pi over 4 into dy by dx here, because what we want then is the value of the gradient at the point then when t is equal to pi over 4. Okay, so just make a note here. So dy by dx here, evaluated when t is equal to pi over 4, that gives us then 2, so I get 2 sec squared of pi over 4, and that's all over them. I mean, I could just simplify this here, right? I could just cancel the 2's, but we'll just continue. I haven't done it anyway, so we'll just continue here. 2 sine pi over 4 cos pi over 4, like so. So evaluate this here then, and what we get for the gradient here is 4, okay? So that's equal to 4 when t is equal to pi over 4. But just be very, very careful here, because what we want then is the equation of the normal to C, right, at the point P. So this gradient here, that would be for the equation of the tangent to C at the point P, okay? So if we want the equation of the normal here to C at P, we want the negative reciprocal of this. So the perp gradient here is -1/4, right? So just be very, very careful for that. So at this point here, we have everything that we need, right? We have the coordinates of P. I've got the value of the gradient at that point, or the negative gradient here. So we're going to use here, so using y minus y1 is equal to m times x minus x1. Just going to use this here then. So I get y minus y1. So y1 here is 2. So y minus 2 is equal to m, which is -1/4. So -1/4 times x minus x1, where x1 is 1/2. Now just be very, very careful here. They want it in this form. So let's just start here by timing through by 4. So I get 4y minus 8 is equal to then, so it's minus x. So just expanding this out here then. So I would get -1 bracket x minus 1/2. So I get minus x plus 1/2 there. Now again, they don't have any fractions here. So let's just times through by 2 here. So what I get here then is 8y minus 16 is equal to minus 2x plus 1. And therefore then, what we can see here is if I add 2x to both sides and add 16 to both sides as well here, what we get then is, let's just do it over here. So therefore then, 8y plus 2x is equal to 17 there. Perfect. As required. So as required there. And we'll give it a smiley face. So as required, smiley face, happy days. We're done. So that's part A done. We've still got part B to go here with a little bit of parametric integration. So as we can see, I don't have much room here. So I'm just quickly pause the video, clear the screen, then we can continue with part B here. So as we can see, then we've now cleared the screen, right? So let's just continue then and finish with part B here. So what we're told then is the region S shown shaded in figure 3, that's this gray region here, is bounded by the curve C, the line L, and the x-axis. So we want to find then using calculus here, the exact area of S. So clearly then we do need a little bit of parametric integration here. So why do I say a little bit of parametric integration here? Well, let me just quickly write down part B here at the very top. What I'll do is I'll do this in a different colored pen. So this question is actually very similar to one of the questions that you got in paper 1. So I don't think you'll get something quite like this, but I've just included it anyway, just because it has a little bit of parametric differentiation, and also it does still involve parametric integration anyway, right? But this question here, what it involves here then is considering the area of a triangle as well. So what I'm going to do here is integrate parametrically from here to here. Okay, that would give me the area under the curve, right? And then what I can see here, I mean, it isn't the case because this line isn't straight, but what I've actually got here is a rectangular triangle, right? So I've got this region here. So the green part we'll find using parametric integration. And then what color should we do this in? Let's do it in, we'll do it in dark red actually. It looks a little bit nicer. And then we've got the area of this triangle here, okay, which we can find using some basic year 2. Is it even year 2? I don't know. Some basic SATs geometry, right? So let's just start with the parametric integration here. So the parametric integration here, don't forget then that the integral here will be, so it's going to be y dx by dt dt. Okay, so y dx by dt dt. Okay, now we did have dx by dt on the screen. I erased that, so let me quickly add that back onto the screen here. So dx by dt, what was that? So just differentiate x here with respect to t. We got 2 sine t cos t, right? So 2 sine t cos t. Okay, y here is 2 tan t. So if we just put all that together then, what I get here is the integral then of, so it's y, which is 2 tan t, and then dx by dt, which is 2 sine t cos t, so 2 sine t cos t, like so, integrating here then with respect to t. We also have limits here that we need to account for, right? So we're integrating between this point here, and it is this point here, right? So from here, like so. So at this point here, that is from 0 to pi over 4, right? As we're told here, this is when the point P has parameter t is equal to pi over 4. So we're integrating here then from 0 to pi over 4. 0 to p over 4, like so, okay? All right, so how do we evaluate this integral here? Well, what I can do here then is just simplify the integrand. So tan t is sine t over cos t. So that means then the cos t here as the denominator would cancel with this cos t here. I've got 2 sine t times 2 sine t. So what we've got here then is the integral then from 0 to pi over 4 of 4 sine squared t. 4 sine squared t there, integrating here with respect to t, right? Like so. Now, at this point here, this integral isn't particularly easy to evaluate. So, is there any trig identities that we could possibly use here that might help us to evaluate this integral? Well, what we can use here is the double angle formula for cosine, right? So, because I've got sine squared t here, I know then, so I'm just going to make a note here. So I'm going to use here the fact then that cos 2t here is equal to 1 minus 2 sine squared t. So 1 minus 2 sine squared t. Okay. So this is 4 sine squared t. So I will add 2 sine squared t to both sides and subtract cos 2t from both sides here. So 2 sine squared t is equal to 1 minus cos 2t, right? Like so. And then if I just double this here, that gives me my new integrand here. So 4 sine squared t is equal to 2 minus 2 cos 2t. Too many 2's. So let's just continue a little bit further down here. We now have the integral then of, so it's from 0 to pi over 4, sorry. Like so. So I've got 2 minus 2 cos 2t, like so, integrating here then with respect to t, right? And at this point here, it becomes a lot easier to work with, right? We can just go term by term here. The 2 integrates to give us 2t. So we get 2t there, like so. The minus 2 cos 2t, just obviously be careful with the sign here. That gives us minus sine 2t because we divide by 2. So get minus sine 2t, like so. And then don't forget your limits here from 0 to pi over 4, like so. Okay. So let's just substitute in here. What do we get? So the lower limit here, that's just going to be 0 because 2 times 0 is just 0. And then sine of 0 is also 0. So the lower limit here does absolutely nothing. So we don't need to worry about that. So for the upper limit here then, I get 2 times pi over 4, like so, minus then sine. So that's 2 lots of pi over 4. So that's pi over 2, right? Like so. So 2 lots of pi over 4, that is pi over 2. Get pi over 2 there. And sine of pi over 2, that is 1, right? So I get pi over 2 minus 1. So that is this green region here. We find the green area. But we're not done here because I also need the red area, right? So for the area of the triangle here, so for the area of the triangle, well, as we said before, it is a right angle triangle. It's a little bit hard to tell because my straight line isn't very straight, but it is a right angle triangle here. So we're going to do base times by the height, divided by 2. So what is the base here? So what I need here then is this point. So that is for 8y plus 2x being equal to 17. As we can see here, that's when y is equal to 0. So I get 2x is equal to 17. And therefore x is 17 over 2. So that's 17 over 2 there. And at this point here, that's when x is 1 over 2. So that's 1 over 2, as we found in part A, right? That was the x coordinate. And this point here is 17 over 2. So what that means here then is the base is 17 over 2 minus 1 over 2. So that's 16 over 2, which is 8. So the base here is 8 units. So apologies, my art skills and my handwriting is just atrocious, but the base is 8 units. I'm hoping that's clear to see. So for the area of the triangle here then, we do the base, which is 8. We times that by the height then. So the height here, we also find that in part A as well. But the point P here, the y coordinate was 2. So the height is 2, right? So 8 times 2. And then we times that here then. Sorry, we don't times that by, well, we can times it by 1 over 2. I'll just divide by 2. Either's fine. I'll just times it by 1 over 2, given that I've already done a multiplication symbol. So 8 times a half is 4. 2 times 4 is 8 there. So the area of the triangle is 8 units squared there. And at this point here, then we can now find the exact area of S, right? So let's just denote this underneath then. So the area of S here, area of S is equal to, so it's the green region here, which is pi over 2 minus 1, plus then the area of the triangle here. So I get pi over 2 minus 1 plus the area of the triangle here, which is 8. If we just simplify this here, then we get pi over 2 plus 7, right? Like so. And there we go. So let's just kind of highlight this here then to indicate that this here is the solution. Lovely jubbly. There we go. So yeah, so a question there on parametric differentiation and integration. These types of questions here are pretty common. As I said, I think the area question might be a little bit different. I don't think you'll be adding or subtracting from a triangle, given that it was in paper 1 pretty much. But just in case then, another question to work through there. Okay. So there we go then. That gives us the solution here to question 13. And then finally, to finish with here, right, we have the very last question for this video, question 14. So deep breath, right? We've nearly made it. Just one more question to go. Now, this question here does cover 2 individual topics of partial fractions and also the binomial expansion. Now, I don't know about you, but I hate the binomial expansion. It's not fun. It's useful, but it's dull. But either way, we do have to answer questions on it. So we can't avoid it, right? So let's just start then with part A here, which is based on partial fractions. So we'll do this right at the top here. So what I've got here is this fraction. So 5x plus 10 all over 1 minus x times 2 plus 3x. And we want to split that then into partial fractions. So if I just start by writing down the original fraction, I get 5x plus 10. So 5x plus 10 all over. So it's 1 minus x there times 2 plus 3x. Okay. And this here then is identical to, so it's going to be a all over the first factor here then of 1 minus x plus b then over the second factor here of 2 plus 3x. Like so, okay? I'm hoping that partial fractions here is pretty straightforward for you, and it shouldn't be too challenging. But in case you do struggle with this here, basically all you want to do then is just get the right-hand side here over a common denominator. So in doing so, what I get here is I get a times 2 plus 3x there, plus b times 1 minus x. Now this here then is over 1 minus x times 2 plus 3x, which is just the same then as the left-hand side here. So what that means then is that the numerators are identical here, right? So we can write here that the left-hand side is identical to this numerator here, so 5x plus 10. Like so, okay? And at this point here then, what we now want to do then is just choose 2 different values of x here to eliminate both a and b separately. So an obvious example here is if I let x be equal to 1, okay? So if we let x be equal to 1 here, what do we get then? So I'll come back to a in just a moment. What happens here then is we get 1 minus 1, which is 0. B times 0 is just 0. So we've eliminated b there, right? And from here, we can go on to solve for a. So I get 2 plus 3 there, because 3 lots of 1 is just 3. So 2 plus 3 is 5. I get 5a then is equal to, so 5 times 1 is 5, plus 10, and we get 15 there. What we can see here then is a is equal to 3. Nice and easy. So now I need to choose a different value of x here. So for example then, if I let x be equal to, so I want to eliminate here this bracket here, right? So 2 plus 3x. So I need to make this equal to 0. So in that case then, just rearrange here, making x a subject. And what I get here is x is equal to minus 2 over 3, right? So x is equal to minus 2 over 3. So if I let x be equal to minus 2 over 3 here, what do we get then? So I get 1 minus minus 2 over 3. So that's going to be 5 over 3 there. So I get b times 5 over 3 or 5b over 3, whichever you prefer. So let me just denote that underneath then. So 5b over 3 is equal to, so this bracket here was 0, right? So that just disappears. And what I get here then is 5 times minus 2 over 3. So 5 times minus 2 over 3. That bracket is atrocious. Let me just quickly redo that. I'm buying a new pen after this video. So minus 2 over 3, like so, and plus 10. So if we just simplify that here then, what do we get? And that's minus 10 over 3 plus 10. So that's going to be 30 over 3. So 30 over 3 minus 10 over 3, that is 20 over 3. So, I mean, you could just use a calculator here. Why am I doing it by hand? I don't know. We'll get 20 over 3. So that's just the same. There's 5b is equal to 20. And therefore, b is equal to 4. And then finally, to finish with here, right, for part A, don't forget to actually write down f of x in partial fraction form. Please don't forget that you will drop the final mark here. So, therefore then, f of x here is just simply this here, but just replace a and b with what we found here. So I get 3 over 1 minus x there, and then b over 2 plus 3x, where b is 4. So 4 all over 2 plus 3x. Perfect. Okay. And there we go then. That gives us the solution here to part A. So for part B then, this is probably my least favorite topic in A-level maths, right? So the binomial expansion. It's not fun. Who enjoys this? It's easy maths, don't get me wrong, but it's not really fun. But anyway, so what we want to do here is find in ascending powers of x up to and including the terms in x squared, binomial series expansion of f of x, give each coefficient as a simplified fraction. So it says hence find. So what that tells you here then is the partial fraction decomposition that we just found in part A will be useful here for part B, right? Because I can now just find then the series expansion here of each individual fraction, add those together, and we're cooking. So let's just start then with this fraction here first. So 3 over 1 minus x here, okay? So as you can see here then, at the very bottom of the page, I have included the relevant result or excerpts here from your formula book. I can never remember this formula off the top of my head, so I've just included it. But we've got it here to hand, just in case you don't have your formula book in front of you anyway. So for 3 over 1 minus x here, well, to begin with, we write this as 3 bracket 1 minus x here to the power of minus 1, okay? So ignore the 3 for now, that just goes on the outside here, okay? What we consider here then is the series expansion of 1 minus x to the power of minus 1. Well, that's nice and straightforward, right? I get 1 to begin with, so 1. I then get n times x here, so that's minus 1 times minus x. Well, that just gives me plus x. I get plus x there. I then do n times n minus 1. So n here is the power, right? So that's minus 1 times minus 2. So that's 2 over 2 factorial, which is 2, so that's 1. And then just get x squared here. So that is going to be minus x squared. So that's going to be positive x squared there. We square the full thing, right? Don't forget. So just get plus x squared there. Like so. Okay, and that just carries on. But we don't really care about anything past that. But just so you are aware, it does continue. But there we go, right? I'm just waffling here. So that's the first series expansion. Nice and easy. So now for the final one here, that is 4 all over 2 plus 3x is a little bit more complicated. So 4 all over 2 plus 3x here. So to begin with then, let's just write it in a similar form here. To get 4 bracket, so it's 2 plus 3x, like so, and that is to the power of minus 1. Perfect, okay? Now, the issue here then is it's 2 plus 3x. I want it to be of the form 1 plus ax. Okay, so what I need to do here then is pull the 2 out as a factor. And once I do that, I raise it to whatever this power is here. So what that gives me then is 4 times 2 to the minus 1, like so. And then pull the 2 out as a factor. So I get 1 plus 3 over 2x here. So 1 plus 3 over 2x there, like so. And that is the power of minus 1. So 2 to minus 1 is 1 over 2. 4 over 2 is 2. So we get 2, and then what I want here is a series expansion of 1 plus 3 over 2x here to the power of minus 1. So again, it starts with 1 here, like so. I then get n times x here. So x then is 3 over 2x, and I times that by minus 1 here. So that gives me minus 3 over 2x. So minus 3 over 2x, like so. I've then got n times n minus 1. So that's going to be minus 1 times minus 2. So that's 2. That's over 2. So that's 1. Well, then what I've got here is x squared. So that is 3 over 2x all squared. So that is 9 over 4 x squared, right? Or 9x squared over 4, whichever you prefer. 9 over 4 x squared. I think that looks a little bit neater. Like so. Again, this does just carry on, but we don't really care. But just to show it anyway. There we go. Okay. So to finish with here then, f of x, right, is equal to, so it's this series expansion here times by 3 plus then this series expansion here times by 2. So what you would get here is, my pen is really annoying me. I'm so sorry. So I know I'm being slightly pedantic, but it is really annoying. So I'm going to get 3 plus 3x plus 3x squared. So 3 plus 3x plus 3x squared. Again, that just carries on, but we don't care. Plus then, so plus here, this series expansion, so that's 2. That's minus 3x. What is this here? So that's 2 times, so that would cancel. I get 9 over 2 there. And so 9x squared over 2, or 9 over 2x squared, whichever you prefer. Like so. And now let's just add these together here. So 3 plus 2 is 5. I've got 3x here, plus then minus 3x. Well, they just cancel, like so. And we've got 3x squared plus 9 over 2x squared. So that's going to be 6 over 2x squared. 6 plus 9, I get 15. So that's 15 over 2x squared. Like so. And there we go then. So that would again carry on, but we don't really care. We're only going up to the terms in x squared. So there we go then. That there is absolutely fine. And that gives us the solution to part B. So the very last part here, deep breath, we're nearly there. So for part C then, we just want to find the range of values of x for which this expansion is valid. So there's 2 series expansions here to consider, right? This series expansion, so 1 minus x to the minus 1. And then this one here, 2 plus 3x to the minus 1, right? So part C, let me just do this underneath here. So for the first fraction here, so for 3 over 1 minus x here, and what I need here, so we need here the modulus of x to be strictly less than 1. So the modulus of x here to be strictly less than 1. That's fine. And now for the second series expansion here then, so 4 over 2 plus 3x. So for 4 all over 2 plus 3x, we need here, so what we need here then is the modulus here of 3 over 2x, so 3 over 2x to be strictly less than 1. So rearrange here, making x a subject inside the modulus then, alongside this inequality here. What that tells us here then is we need the modulus of x here to be strictly less than 2 over 3, right? Times both sides by 2, divide by 3, like so. So therefore then, the range of values, so the range of values here of x for which the expansion is valid, expansion is valid is, so what is the solution here? Well, it has to be this one, right? Between minus 2 over 3 and 2 over 3, right? So in that case then, let's write this down as it is, right? So minus 2 over 3 up to 2 over 3. And there we go. That is the solution to part C. This here was the solution to part B, and this here was the solution to part A. Hopefully you can kind of decipher everything on the screen. I apologize for my handwriting on my presentation. It's never the neatest. And apologies for my pen. It's really annoyed me. I'm going to go and buy a new pen after this video. But there we go then. So that gives us the solution here to the very last question for this video, question 14. As I mentioned in the introduction, right, we didn't quite cover absolutely everything. We are missing a question on vectors and arithmetic series, recurrence relations, sigma notation. So those two kind of like big topics there are the only thing that are really missing here. So I am hoping that this video here will help in your last minute revision for paper 2. Don't forget, guys, if you are looking for any last minute revision here for A-level maths, right, head over to our website, AJMaths.co.uk. We have worksheets, additional revision videos, mock and predicted papers there for A-level maths, right? So there's 10 predicted papers over on the website at the moment. And we will be adding paper 2 very, very shortly for this year's exam series. So go and check that out if you are looking for any last minute revision here for A-level maths. And I think that covers everything. So there we go then. That brings us to the end of this last minute revision video here for paper 2. If you made it to the very end here, then well done. This is a very long video, and I am hoping that it has helped, right? Thank you so much for watching. Best of luck with paper 2 next week. And yeah, take care.